Yesterday I was partway through the section on odds ratios when I came to the end of the lecture. Today I'll finish off that section. So I'll be starting top of page 84, section 4.4.2 in the printed notes. So to remind you of where we were, we're assuming here that we've got a binomial generalized linear model, and we're fitting it with a logit link. Okay, so the fact that we're fitting it with a logit link here is useful for odds ratios because we can naturally calculate them from the parameters of the logit regression in the way that we see here. So because in a logit link, the linear predictor is actually equal to the log odds corresponding to the probability of success in our model. That means that if we take e to the linear predictor, that actually gives us the odds. So we can write the odds, and if they're estimated odds, there would be hats on these betas. So we can take odds ratios by looking at ratios of terms which look like this. And if we say are interested in the odds ratio for one variable being bigger by one of the x's being bigger by 1 than in the other model, then that just simply corresponds to e to the corresponding beta term. So odds ratios in logit binomial GLMs can be obtained by taking the exponential of the parameters that are estimated in the model. Okay, so I'd already done an example with a factor with 2 levels. So this was a data set that I introduced at the end of yesterday's lecture. So this is a data set on coronary heart disease. So there are 4 columns in the data set. So the first one is the response variable, the status. So that's 1 if the patient has coronary heart disease and 0 if they don't. And then the potential explanatory variables in the data set are 1 on the level of fat in their diet. So 0 indicated a low fat diet, 1 a medium fat diet, and 2 a high fat diet. Gender, so 0 for female, 1 for male, and finally age in years. So we're going to be working with this data set today. You're not sure about something? Okay, so let's focus specifically now on the saturated fat variable. So we can estimate odds ratios for the different levels of fat in the diet by fitting a generalized linear model which has the response variable as status and just puts the saturated fat values as the explanatory variable. So at the moment, we're ignoring age and gender here. In yesterday's lecture, we had one where we just had gender in the model. Now we've just got saturated fat in the model. Saturated fat is a factor with 3 levels, 0, 1, and 2. So I think it makes sense to treat it in this way rather than to treat it as those variables as having numerical significance. So there's no particular reason why the effect of high should be twice the effect of medium. Okay, so I fitted it as a factor in my R code here, and it's going to be binomial. The default link with binomial GLMs is logit, so we don't need to specify that it's a logit link. And the CHD is the data set. So here's what we get. We see our estimates for the parameters for saturated fat, and these are for levels 1 and 2. So on the next slide I'll say a little bit more about what those mean. So those are our estimates, and we see that both appear to be significant according to R. Okay, so what's the actual linear predictor here? Well, because we're fitting using a factor with the saturated fat, it has 3 levels, 0, 1, and 2. Remember that corner point constraints, as we called them, made the coefficient of the first level, level 0 here, 0. So we have indicator variables for saturated fat level being 1 or 2. Okay, so our linear predictor will take the following form. It'll be beta 0 for somebody with a low fat diet. It'll be beta 0 plus beta 1 if xi is 1. So they've got a medium fat diet. And if they have a high fat diet, it'll be beta 0 plus beta 2. So somebody with a low fat diet will have linear predictor beta 0. Medium fat, it'll be beta 0 plus beta 1. And high fat diet, it'll be beta 0 plus beta 2. Okay? So that's what the linear predictor actually means here. So if we want to look at the odds ratio for getting coronary heart disease, and we want to compare for the difference between a medium fat diet, which corresponds to xi being 1, and a low fat diet, which corresponds to xi being 0. Okay, so for a low fat diet, the linear predictor is beta 0, so the odds will be e to the beta 0. For the medium fat diet, the linear predictor is beta 0 plus beta 1, so the odds will be e to the beta 0 plus beta 1. So the ratio between the two odds will be e to the beta 0 plus beta 1 divided by e to the beta 0, which is e to the beta 1. And if we want an estimated odds, then we need to use our estimate of beta 1 here. So e to the beta 1 hat. Now, if you look back to the estimates on the previous slide, our estimate of beta 1 is given in the R code. It's the estimate here for the factor level of the factor being 1. So it's this 1.3981, which is what you saw on the next slide. Okay, so we get e to that estimate, and that gives us just over 4. So the odds ratio for a medium fat diet compared with a low fat diet is estimated here as being a little bit more than 4. Okay, now we can do the same thing for the other combinations of difference between the diets. So if we're looking for comparing a high fat diet to a low fat diet, we're going to get e to the beta 2 hat, where beta 2 is the estimated coefficient for a high fat diet. If we want to compare a high fat diet to a medium fat diet, then for a high fat diet, the linear predictor will include beta 2. For a medium fat diet, it will include beta 1 instead. So if you look at the ratio there, you'll get e to the beta 2 minus beta 1. And again, because we're estimating these, we put hats on them to indicate that those are the estimated. It gives us the estimated coefficients, so that gives us the estimated odds ratio. Now in that case, we see that it's actually quite close to 1. Now an odds ratio of 1 would say that the odds were the same, so the probabilities were the same. So it would suggest there possibly isn't that much difference between a medium fat diet, which is xi being 1, and a high fat diet, xi being 2, in this data set. Okay, so that's what we can do with a factor with multiple levels. So we can also work with a continuous variable, so for example, the age variable in this data set. Okay, so here, if we've just got the age variable in the data set, our linear predictor is going to be alpha plus beta xi. So alpha is the linear term, so the constant term, and then beta xi, beta is the coefficient of age here. Okay. So what happens if we look at two patients, one a year older than the other? Okay, so one has xi and the other one has xi plus 1. Okay, so that's 1 year older. So that changes the odds from what we've got here, e to the alpha plus beta xi. Over here, we now have e to the alpha plus beta times xi plus 1. Okay, so those are the odds if the patient has age xi plus 1. These are the odds if the patient has age xi. Okay, so if we want to look at the ratio of the odds for the difference of 1 year in age, then we can simply divide that by this one. And if we get that, what are we going to get? We're going to get e to the beta. Okay, because the alpha and the beta xi terms will cancel, so we just get e to the beta as our odds ratio for getting coronary heart disease, given that somebody is 1 year older. Okay, so again, we can do that in our data. We can fit the model in R, so we're now fitting status modelled by age, just age alone, and everything else is the same. Then this is the model that we get. So we get the coefficient of age being about 0.055. Again, the modelling says that that's significant. We can work out the odds ratio as e to this estimate here. This is obviously our estimated odds ratio, and here it comes out as 1.06. So that's saying the estimated odds ratio for given somebody is 1 year older is 1.06. Okay, so every year older, the risk of coronary heart disease increases by 6%. And you can do this for longer periods of time. So that's the odds ratio for 1 year. For a larger number of years, you just take that odds ratio and you take it to the power of the number of years. So for 10 years, you would want 1.06 to the 10. And so the odds ratio 10 years older, 10-year difference of age, the odds ratio is then 1.73 for getting coronary heart disease. Okay, so over the end of yesterday's lecture and the beginning of today's, we've seen now what to do with each variable individually. But what about if we want to consider them together? Okay, so now we have multiple explanatory variables. Okay, so now we are going to want to fit this model with all three of these explanatory variables included. Okay, so let's consider one particular one of our variables. So let's say the one that we've got the coefficient for is going to be beta 1. And we consider what happens if we increase it by 1. Okay, so our linear predictor is, so alpha, which corresponds to what I called beta 0 on the board, but it doesn't matter, e to the alpha plus beta 1 times xi1 plus 1. That's now with the new value xi1 plus 1. So this is what we get if that variable 1 is increased by 1. These are the odds which are e to the linear predictor. Okay, so if we just want to compare what our odds are for making just this change, increasing the value of variable 1 by 1, the original odds would be the same here, except that they just have xi1 here. Okay, so those are the original odds with the original xi1. So if you increase that by 1, the only change is that you get that xi1 plus 1 there. So if you look at the ratio of those two odds, everything else cancels, and you're just left with e to the beta 1. Okay, so for a unit increase in variable x1, the odds ratio for getting coronary heart disease, or whatever the thing in the model is going to be then e to the beta 1. Okay, so people doing epidemiological studies call this adjusting for the other variables in the model. Okay, so let's look at what we get for the coronary heart disease data. And let's say we're interested in the male-female comparison. But we now want to include the information about age and diet in our model. So we're adjusting in that terminology for age and diet. Okay, so here is what we get if we try and fit the model including all variables. So status is now fitted as age plus factor of gender. So gender and saturated fat are both factors, so that's been included in the coding. Otherwise it's the same. So again, it's a binomial GLM with the default logit link. Okay, so we get estimates for all of our parameters. So there are 5 parameters that we estimate here: the constant term, coefficient of age, coefficient for being male, which is this one, and then here we get coefficients for medium fat diet and high fat diet. You might notice something if you look carefully at those numbers, which is a little bit surprising. Okay, so what we want is we're trying to find the odds ratio for getting coronary heart disease for being male rather than female. So that corresponds to gender being 1. So our estimate of the relevant parameter, the relevant beta parameter, is this one. It's 0.83048. So to get the answer, we just need to take the exponential of that value. Okay, so our estimated odds ratio for males compared with females, adjusting for age and diet, is e to that estimate, which turns out to be 2.29. When we didn't adjust, when we had left saturated fat and age out of the model altogether, we got 2.23. So it hasn't actually made that much difference in this case. Our estimated odds ratio is quite similar in the 2 models. Okay, however, you can get situations, particularly if you have quite heavily correlated variables around, where you do need to, you certainly do need to adjust, and doing so can make quite a big difference in the estimated odds ratios. Okay, finally for chapter 4, we can also do confidence intervals for odds ratios. So if we're trying to work out a confidence interval for an odds ratio, then we can note that for log odds ratio, we can just use the estimates in the R output, and remember that those estimates had a standard error. So if we, for example, want to estimate our get a confidence interval for the odds ratio for gender, just as the thing we just calculated, this is our estimate, 0.83048, and this is our standard error for that estimate. So we can just simply calculate a confidence interval for the log odds by taking this value as the center point and going for your standard 1.96 if you want a 95% confidence interval, times the standard error on either side. Okay, so these things have asymptotic normal distributions, so the 1.96 is right. Okay, now you can see from the fact that the Z value is given as 1.969 that this is going to be very, very close to including zero, but not quite. Okay, so what we get is that center value, 0.830, plus or minus 1.96 times our standard error estimate. And if we do that, we get something very slightly bigger than 0, 0.004 to 1.66. So that's a confidence interval for the log odds ratio. So it's easy enough to transform it into an actual confidence interval for the odds ratio by just taking exponentials of each endpoint. So if we take the exponential of the left-hand endpoint, we get 1.004, and if we take the exponential of the right-hand endpoint, we get 5.24. So that's a 95% confidence interval for the odds ratio. Probably again worth saying that the asymptotic theory here is usually approximate for generalized linear models. So if you're really bothered about whether one is in this interval or not, it's very close to being in it. Saying definitively that it isn't is not clear when it comes as close to 1 as this. Okay, so that finishes chapter 4. So I'm now going to go through chapter 6 in the notes. So this is pages 90 to 92 in the printed notes. So hopefully I will have time to give a reasonable description of what's going on here today. Okay, so generalized linear models, when we introduced the standard form for a generalized linear model, we had a number of parameters in there, which included something which we called phi, which was a dispersion parameter. And we observed when we tried to get the binomial distribution or the Poisson distribution into the generalized linear model form, that phi turned out to be 1. So the dispersion parameter for a binomial or Poisson model is 1. Now, sometimes you get situations where a binomial or Poisson seems to be a reasonable modelling assumption. However, if you look at your data, it turns out that the variances seem to be bigger than a binomial or Poisson model suggests that they ought to be. This is something that can happen quite often for various reasons. So, there are various approaches to dealing with this problem. One of them, which can be fitted within the generalized linear model framework, is to assume that in fact the phi that appeared in the generalized linear modelling assumptions is not 1. To assume that it's now an unknown parameter, as it could be for some other generalized linear models. Okay, so for the binomial, the variance is mu I times 1 minus mu I over ni. So that's what we had for the binomial variance. And for the Poisson, it's simply mu I. Okay, so what we can do is we can assume that these still hold, except that we multiply these variances by phi. Okay, so that's what we're going to do. And it turns out that you can fit the model in the same way. Estimating phi. So at the end of chapter 3, there was a little bit on estimating phi, and so we can do that here as well. Okay, so the situation that I described, where the variances appear to be bigger than they should be for a binomial or Poisson model, is called over-dispersion. Just possibly, you might find yourself in a situation where the variances seem to be too small for a binomial or Poisson model, which would be under dispersion, and this allows for that as well. Okay. One other thing is that these models that I'm going to describe can be used if you have your data which doesn't obey the constraints that binomial or Poisson data have. So for Poisson data must be integer valued. For binomial data, the number of successors in the data in each observation must be an integer. Now, of course, the data we actually fit is the proportion of successors. So the proportion of successors times the weight, which is the number of trials, that must be an integer. Okay. So, because we're now multiplying our variance function by phi, so the variance functions we had for the binomial or Poisson, and we're not making other assumptions about the distribution. So for the binomial and Poisson, these variances come from the formula that you get for a binomial or Poisson distribution. If you assume those formulae for the distribution, you're not going to get these multiplied by phi, you're going to get these on their own. So if we're just making assumptions about the mean and the variance, we don't have a specified probability distribution. And because we don't have a specified probability distribution, we can't write down a likelihood. Our only assumption is about the mean and the variance of the distribution, so we don't have likelihoods. So it seems that our methods for fitting generalized linear models and for doing tests which involved likelihoods and which involved generalized likelihood ratio tests, seems like we can't do those if we don't have likelihoods. Okay, it turns out that you can get away with this because there is something called a quasi-likelihood, and you can use techniques based on quasi-likelihood to show that in fact the generalized likelihood ratio tests can be applied in this setting. So I'm certainly not going to spend time in this lecture going through the details of why this works. Essentially, I'm just going to tell you this theory of quasi-likelihood exists, and it allows you to use generalized linear model type methods if you have these as your assumptions. Okay, so let's now focus on the binomial distribution. So remember that the binomial distribution crops up if you have ni trials and they're independent and they have constant success probability pi. Okay, so that's the assumption that gives you a binomial distribution for the number of successes. Okay, so what happens if the assumptions go wrong? So one possibility is that the success probabilities are not in fact the same in each trial that's in the same group. Okay, so because they're in the same group, they'll have the same regressor variables, but there might be something else about the individual trials, which means that the success probabilities aren't constant. So, I mean, for example, in these beetle data sets, we're going to see another beetle data set in a minute, the underlying health of the beetles before they were put into the trial might affect how likely they were to be killed in the toxicity test. So, in that situation, the values wouldn't all be the same. So in that case, you don't get a binomial distribution anymore. Okay, so that means that our original variance formula for the binomial isn't going to be valid. Okay, and what you tend to expect then is you get a higher variance. Okay, so what we can do is we can scale the variance by, as I've said, multiplying it by this unknown phi. So over dispersion, which is what would apply in the situation I just described, would correspond to phi being greater than 1. Phi being less than 1 would be under dispersion. It's quite hard to think of a scenario where under dispersion makes sense. So non-independence of the trials is another way that this can happen. Okay, so as I've said, the assumption that we're making here is really just an assumption about the means and the variances. And it's saying that the variance depends on the mean in this way with some unknown phi. So we're not specifying a probability distribution anymore. Okay? So we can't use a standard likelihood. However, we can appeal to this theory of quasi-likelihood, and that allows the theory of generalized linear models to be used. Okay. So we'll estimate phi by dividing the Pearson chi-squared statistic by the number of degrees of freedom, as described at the end of chapter 3. There's an aside in the notes which mentions another possible way of dealing with this situation, which is to use regression based on another distribution. One distribution which can be used, particularly in the situation where the trials are not independent, is to use what's called a beta binomial distribution. And this is where you have a binomial distribution, but the parameter itself is random and has a beta distribution. And so this beta distribution coming in allows more variability in the values than you would get in a standard binomial. So you can use a beta binomial model, and there are packages for R which will allow you to do regression with beta binomial models. So that's another approach. Okay, so let's talk about this example. So as I said, I'm afraid it's going to be another toxicity trial with beetles dying. So the experiment was on grain beetles, and it was ethylene oxide that was being tested. So there are n beetles in each one exposed, and SI is the number which died. Okay, so we've got various ranges of our xi. So xi is the concentration here, I think. Yeah. So it's the log of the concentration. Okay, so here are some plots. So the plot on the left shows the untransformed data with the circles. The crosses are the fitted values for a model that we will describe in a minute. The picture on the right is a link checking plot. So back in chapter 4 we were thinking about how we'd try various links for binomial models. So here this is a plot of the probit test against the log, and you can believe that that is a plausible straight line, although it's quite noisy. There's quite a bit of variation around the straight line in that picture. Okay, so left plot, observed proportion by log concentration. So that plot itself, the one, the raw data, that actually looks reasonably linear. So you might actually say, well, let's just use a linear model. We don't need to go into generalized linear models and link functions. However, it's clear that if we did that, if we made the concentration big enough, a linear model would predict that the probability would exceed 1, probability of the beetle dying. So if we use our standard link functions for binomial responses, we won't get that problem. We'll get probabilities between 0 and 1 for all values of the log concentration. Okay, so if we look at the probit test, as I've said, it looks reasonably linear. So that looks like a binomial GLM with a probit link would be a good place to start. Okay, so here's our here's some R code that will fit that model. So GLM, so S over N here is to get the proportion, and we're just, and X here is the log concentration, so S over N as a model for model by X, binomial GLM, probit link, and n here are the weights. Remember that for a binomial GLM, you need to include the weights in your R code. Okay, so what do we get? So null deviance. So there are 10 data points here, so 9 degrees of freedom for the null deviance. We get a pretty large value, 138. Okay. If we use a linear predictor, so just the obvious one, so beta 0 constant term plus a linear term, beta 1 times the log concentration. So probit link, we get a residual deviance of 35.476. You can also work out the Pearson chi-squared, which is a little bit smaller, 33.18. Now, degrees of freedom here, 10 data points, and we've estimated 2 parameters, so there are 8 degrees of freedom here. Okay, so if we look at the change in deviance between the two models, so that's the difference between that 138 and this 35 here, that's big. Okay, we've got a large change in the deviance between the two models, 1 degree of freedom, so we can compare that with the chi-squared 1, and that's an enormous value on a chi-squared 1, so we have very strong evidence that the second model with this linear term in it is better than the null model. However, these numbers are quite high for a chi-squared with 8 degrees of freedom. So if we look at a chi-squared with 8 degrees of freedom, we can work out the p-value by that code. So 35.476 was our output residual deviance here. 8 degrees of freedom, we're getting a really quite small value. So that would be the p-value for the test with the null hypothesis that linear model is appropriate. Okay, so we seem to have evidence here against the binomial model with the probit link. So you could ask, are there other things that were not taken into account that we haven't seen in the data set? Would a different link be better? Unfortunately, the answer is no to both of those questions. If you look at other links, you don't find anything any better. And there simply weren't any other possible explanatory variables. You could try polynomial terms, so you could try and fit a quadratic or something like that, or even a log. However, if you look at the actual results that we got, the plot against the probit, it looked like it's a straight line. So there's really no reason to think that that's going to help. So it looks like there's a genuine problem with the binomial model here. So in the plot that was a bit further back, the fitted values from this probit model were the crosses in that plot. Okay. So that suggests that we might like to consider, because our deviance looks too high for a binomial model, we might try to fit an over-dispersed binomial model. So how do we estimate phi, the dispersion parameter? Well, the way that R does it is to take the Pearson chi-squared statistic and divide by the number of degrees of freedom. Okay, so we get a phi value of about 4. And if you do that to do that in R, you replace the binomial in the R code by this quasi-binomial. So quasi-binomial in R will fit a generalized linear model with a binomial type link and with the same, it's basically maximizing the same likelihoods as for the binomial. However, it then estimates phi. It doesn't assume that phi is 1. It estimates phi using this Pearson chi-squared method. Okay, now, because we've changed the value of phi from 1 to this bigger value, that means that we change the standard errors of our estimates. So all our standard errors are multiplied by the square root of phi. So that means they're quite a bit bigger. Okay, so we can again compare the original null model with the model with a linear term in it in this quasi-binomial setting. Now, the residual deviance given by R is the same. However, the theory tells us to use the scaled deviance, for which we need to divide by phi. So the difference between the two deviances, when they're scaled, is now the original difference between the two deviances, which was this 102 here, divided by the estimate of phi. Okay? Perhaps in principle we shouldn't be using the estimate, but the estimate is all we've got. So we divide by the estimate of phi here, and we get this 24.72. That's obviously still quite a large number for a chi-squared with 1 degree of freedom. So even with this estimation of phi in this quasi-binomial model, there is still good evidence that the model with a linear term is better than the null model. However, you should note what's happening here, that the change in scale deviance is being reduced considerably by the fact we have to estimate phi. So if you're estimating a large value of phi, then your differences in scale deviance are going to be substantially smaller than if you'd been assuming phi was equal to 1. Okay. We can calculate the scale deviance. So we take our original scale deviance and divide it, our residual deviance, sorry, for the linear model, and we divide it by phi. And we get something a little bit more than 8, so we get 8.55. Now, formally, we've estimated phi here, so that suggests that we've lost a degree of freedom, so now have 7. That looks quite good. 8.55 is quite close to 7. However, there's a warning here. Our estimate of phi was based on the Pearson chi-squared. The chi-squared is similar to the deviance, the residual deviance. So this is actually almost fixed in such a way that we will get a value close to the number of degrees of freedom if we do this. This is really just confirming that we've done the calculations correctly, rather than telling us that yes, there really is no evidence against the model. Okay, so we can do some more checks. So we can, unsurprisingly, given the high chi-squared value on the previous slide, we can see that the beta estimate of beta 1 appears to be significant because our t value turns out to be 4.325. So that's using the world test statistic. Because its standard error was 2, so obviously the standard error would have been quite a lot smaller if we hadn't estimated phi. So the evidence is still coming out that this is significant. Okay, so one point is that the fitted values themselves don't change here. If you look back in chapter 3, you'll see that the estimates of the parameters, the betas, in the linear predictor, those are the estimates of those are independent of the estimation of phi. So you get the same estimates of the parameters in the linear predictor, whatever your estimated value of phi is. So if you're assuming phi is 1, you get the same estimates of the betas as you do for a different value of phi. So the fitted values don't change, and so the residuals don't change either. Okay? What having this larger value of phi does is it allows the model to essentially fit better because it's allowing a larger variance than the original model was. Okay, there is a bit of a health warning here. You can end up essentially overfitting the data in this situation. The particular data set I've just gone through is one where there really is quite good evidence that there was something wrong with the original model. Those deviance and Pearson chi-squared values were very high for a binomial model. Here the value of phi is quite large, and so there is quite good evidence for it. So one rule of thumb that some people suggest is that if your estimate of phi is less than 2, then you should probably stick with your original model with basic binomial or Poisson. Okay, so just to finish, you can do this with Poisson as well. So then you've got the variance of yi being phi times the mean mu I. And you estimate phi in the same way. Quasi-binomial is what we used for the data I've just been talking about. Quasi-Poisson is what you now use if you're using a Poisson-type model with potential over-dispersion. And you don't need these to be count values. They just need to be non-negative data. So it can do this even with values which are not integers. Okay, that's time up for the module, or for MSc students, the first half of the module. Thank you for listening, and to be continued by Professor Wilkinson for the MSc next semester.